Welcome everyone. Talk today is about breaking Azure AD joint endpoints in zero trust environments. Really excited to be back in a physical conference. It's really good. I hate online conferences. So thank you all for being here. A little bit about myself. I'm Dirk Mollema. I live in the Netherlands and I do a bit of a mix of penetration testing, red teaming and security research. I like to write tools that help me doing my work better. And well, some of the better known tools are MinIM6. I wrote Python port of the Bloodhound gatherer. And for Azure, I also wrote ROTools, which is one of the Azure tools. I have a blog and I have a Twitter account where I write about my research. Today, I want to get started with talking a bit about Azure AD, what it is, and Zero Trust, really short. And then we'll dive into the technical content, looking at Azure AD device join, how it works and what it does, and how trusted platform modules or hardware-based security plays into that. Then we'll start a topic about primary refresh tokens, how we can interact with them from an attacker's perspective, and what fun stuff we can do with it to play. We'll talk about registering devices in Azure AD on a less official way. And as a bonus, I'll talk about bypassing multi-factor authentication if you're an Intune admin in Azure AD. So just to make it clear, today we're talking about Azure Active Directory, not to be confused with on-premise Active Directory. It's completely different, even though it's called partially the same. But if we're talking about Azure AD, it's really the identity platform for all of Microsoft's online services. So that's Office 365, but also the Azure Resource Manager where virtual machines are stored. They all use Azure AD as a identity platform. And also other third-party SaaS applications that you can integrate with it. You can have the authentication done by Azure AD. So we're not talking about infrastructure as a service, or platform as a service, or virtual machines in Azure. This is really about the identity part. We'll also be talking about Zero Trust. It's a bit of a buzzword, but in the end, Zero Trust, at least the way that Microsoft explains it, is really about combining identity information. And that can be from user identities, so that's what you see on the top, and also a device identity. So the idea is that if you combine those two, then a user is using authentication on hopefully a trusted device, and based on that, Zero Trust can make decisions whether or not you're allowed to access, for example, sensitive information. So of course, user identities is a fairly well-known topic, all with the passwordless and Windows Hello, very interesting. But what's a bit less well talked about is device identities and how they play into this whole thing. So device identity is really a device that is registered or joined to Azure AD. Now, device identity doesn't necessarily have to be a Microsoft product or Microsoft physical product. It can also be your mobile phone, or it can be, for example, a macOS laptop that's joined to Azure or registered in Azure AD. And when these are registered in Azure AD, they have a device object. So it's like an identity object, but then for a device instead of a person. And of course, devices that are in Azure AD can be managed by a mobile device manager, such as Intune. So there are a couple of options to register your device in Azure AD. I think the full or the modern new option is Azure AD joined. Then a device really only knows about Azure AD. It's not linked to any on-prem stuff anymore, but it's only for Windows 10. So it's supposed to be used for corporate-owned devices, and they're fully managed and joined to Azure AD. There's also like a bit less strict variant, which is Azure AD registered. That means that the device isn't fully managed, but only part of it is managed. You could, for example, do this for bring your own device, or on Android or iPhones, you can have like a container within which the work data is stored, and then that part is registered in Azure AD, but it doesn't necessarily mean that you have to manage the whole device. And this is also compatible with more operating systems rather than just Windows. Lastly, there's also a hybrid join, which is a bit of a mix match of old and new. So these are primarily joined to an on-premise Active Directory domain, but they're also synchronized to Azure, and they also have an identity in Azure AD. These are not managed by an MDM solution, but are usually managed by the on-prem ADs or via the well-known group policy objects, for example. In this talk, we'll mainly focus on Azure AD joint or hybrid joint. Azure AD registry works slightly different, but the concepts do have some overlaps. So the device joint flow, how does it actually look? Well, when you buy like a new Surface, for example, laptop, and you set it up, you get this screen, and it prompts you to sign in with your Microsoft account. And if it's an enterprise edition of Windows, it will ask you to log in with your work account. So if you do that, then you go through the whole flow, and then your device is automatically joined to Azure AD. You can also do it for devices that are already set up. So when you have that, you can go to the option to access work or school, and then choose to join your device to Azure AD. But it's not, well, it works a bit the same, but one is before setup, and one is when you already have a device. In the background, what it does is it prompts you to sign into your Microsoft account. And using that sign-in data, it requests tokens for the Microsoft device registration service. And once you've got a token and you can access that service, it gives you like the final prompt, like, are you sure you want to join this device to this organization? And then you click join. So what happens at that point in time? Two RSA key pairs are generated. So public key and private key. And one is the device key, and one is the transport key. And the device key is really used to identify the device as an entity. And the transport key is used to encrypt sensitive data while it's in transport between Azure AD. So the device key can prove the device identity, and the transport key can be used to transfer sensitive material. The public key for this is sent to Azure AD, and the private parts of these RSA key pairs remain on the device. How does this look? All right, so here's a request. I hope it's a bit readable in the back, but we'll go over it bit by bit. So this is basically the whole Azure AD thinks they're all APIs, they're all web-based APIs, and this is basically a simple post request to the enterprise registration service. Of course, the first part is the access token for the service. So that's when you signed in, you provided your information, and you get back an access token that proves that you are actually have access to that account. So that's used for the authorization. Then there's a certificate signing request. That's really normal certificate signing requests, as we see in public key infrastructure as well. And it's basically the device asking Azure AD, hey, I've just set this up. Can you please sign my certificate so that it can be trusted in the future? Next to that, there's a transport key, which is the public key part of the transport key, so that Azure AD has the public key and it can encrypt information with that when it wants. There's also, of course, some information about the device. Funny enough, if you play with this, you can call it anything you want. So it could also be, I don't know, it could say I'm a shoe or something, version 10, and that would work. So it's not really strictly checked, but it's just used to populate the information in Azure AD. The join type is in this case 0. So the join types, there are different join types that we just talked about, and 0 is an Azure AD join, and there are different numbers for the different join types. And lastly, there's a device ticket, which is used to prove some different part of the device identity, which is not really important for this talk, and it's also not required, so you can just leave this out if you want. What happens then in the backend? So Azure AD then gives a certificate, and that certificate is signed by the certificate authority, and then you have your device certificate. And there's also a device object created in Azure AD. So if you go to the Azure portal, you see like the device with the host name and the Windows version, and you see the join type is Azure AD joint, so it's officially joined to Azure AD. For those that are familiar with this whole flow, you can see that the MDM is here set to none. So when you join an Azure device to Azure AD, it doesn't automatically register it in Intune. So that step is distinct from that. So there's no link with Intune yet at this point. What you get back is hopefully a 200 OK from Azure. with their certificate, thumbprint, and of course the certificate that's signed by Azure AD, as well as some of the membership changes. So when you join a device to Azure AD, different users and different groups get added to the local administrators group on the device. Normally that's the group ID of the global admins and of the device administrators. And these all have security identifiers, just like you would normally see on Windows. And if you then request the status of the device, you can see that it's Azure AD joined. It's not domain joined, so it is a hybrid joined device. And on the bottom, we see that we have a device ID, and we have a certificate, and we also see that this certificate is protected by a TPM, which we also can see from the key provider, which says the Microsoft Platform Crypto Provider. So the platform crypto is usually associated with something hardware, where the software provider is like software stored on the device. So in this case, some of the private parts of the key are protected by a TPM. Now, what is a TPM? So fully said, it's a trusted platform module, and it's supposed to be a separate processor or a separate part of the processor in which you can store secure data. And this can be a physical chip, for example, on a desktop computer. On the picture, you see one that you can plug on the motherboard. It can be integrated in your CPU, or it can also be virtual. Basically, most modern processors do have a virtual TPM, so they have this secure storage area. It's also a requirement for Windows 11, probably because Microsoft really wants this security boundary to be enforced in Windows 11, and they want to securely store these device identities somewhere. Because the idea is that if it's in a separate chip, then the operating system never has access to the private key material again, so it cannot leave the device. So I made a little drawing. The private key can either be generated on a TPM or put there. And after it's in the TPM, which is of course part of the device, it's not like on a USB dongle or something, then the OS can no longer get the private material out of the TPM. What it can do is ask the TPM to use the private key material. So for example, if they want to calculate an RSA signature, they can ask the TPM, hey, can you just sign this for me? And then the TPM will give you back the signed information without disclosing the private key itself. So it's really to keep things separate from the operating system. Now, there's a few things about TPMs that are important. What it mainly protects against is like two scenarios. So one is if you use your TPM to store like, for example, your BitLocker key, then the scenario is if someone steals your device, they cannot extract that material from the TPM, at least if it's protected by something like a PIN or a password or something, then it's protected in the TPM. The other thing is it shouldn't allow you to extract private key material while you're running on the operating system layer, because it's a separate hardware module and you're not supposed to extract private material from there. What it doesn't protect against are like physical hardware attacks. So there are some scenarios known in which you can just like sniff the pins of the TPM, and whenever the exchange is made, for example, for the BitLocker key, then you can extract that. So that's not something that it's supposed to protect against. And also, TPM does not prevent you from actually using the key material that's in the TPM. Like if you're on the operating system, you're running a system, you can ask the TPM to do whatever. And if you want to sign like 1,000 requests, the TPM will happily do that. It only prevents you from extracting the actual material and sending that somewhere else, for example. So it's supposed to stay on the same system, but it's not supposed to protect you from actually using the material while you have high privileged access to the device. So whenever a device is joined, then this private key material is stored in the TPM, if you have one. If not, it's stored in software that's less secure. But after the device is registered, then there's key material for the device identity in the TPM. Now, we have the device registered, and then the user signs in for the first time. So they use the username and password, and then Azure AD gives you a primary refresh token. And the primary refresh token is really also like a persistent piece of identity. So for anything you access in Azure, you can use this primary refresh token to prove that you're that identity without having to enter your username and password all the time. So let's see how that's issued. How this works is first that the device is actually requesting a challenge from the server, from Azure AD basically. That's just because it wants to have a nonce to prevent against replay attacks, so it doesn't. It's not something that's the same all the time. It simply asks you, hey, give me a challenge that I can do something with. Azure AD will then just give you a challenge, and it's basically in the form of a nonce. The nonce is some part of encrypted data. I think it contains at least some form of timestamping, but no way sure because Microsoft has the private key to decrypt the nonce and actually see the information that's in there. But it's not like a fully random string. But we can use this nonce, and with the nonce and with the private key, you can generate a piece of data, then sign that, and then Azure AD will accept that as coming from the device. How does that look? So it's just sent a request to the server, and if you're familiar with the OAuth things, then you see that there's a grant type, which is a special one. It's a JSON Web Token bearer, and there's some request which contains a lot of gibberish. It's actually a JSON Web Token that's in this request, and if we decode that, we see some data in there. So we see the client ID, which is our device ID. We see the nonce that we requested. We see some other parameters like scope and the group identifiers. And most importantly, we see that the passwords that the user just entered is sent to Azure AD. So basically, it takes the username and passwords, it puts that in the JSON Web Token, which is signed by the device key. So it asks TPM to sign this part, and then it sends that off to Azure AD. Azure AD can then verify that this was signed using the correct private key because it has the public part that was sent to it when it requested the certificate. So Azure AD can verify this came from a legit device, and it can issue a primary refresh token. Which is really just like a regular refresh token. It's a JSON Web Token, it's encrypted, you can't really see what's in it, it's one big secret. But it's here basically, and this is really the part that's really important because this is a token that's valid for 90 days, and it will give you access to anything in Azure AD as that account. So it's a very important piece of information. It is, however, not really secret by itself, because the primary refresh token is only a token. It contains information, but just having it doesn't really prove anything. The important part is that you have the session key. And this is the session key, which is encrypted. So the device can decrypt that using the transport key that it generated earlier, and then it has the session key for the primary refresh token. And the combination primary refresh token session key, that is what can be used to sign in. There's also some expires in, which is actually inaccurate because it says here that this is 14 days in seconds. And Microsoft finally updated the documentation to mention that it is actually 90 days. So this is valid for 90 days if you don't renew it. So to summarize what we just learned, there's a private key for the device, there's a transport key, and there's also the session key for the JSON Web Token. These are all stored in the TPM. So you're not supposed to access that anymore. The computer can use the keys, but it cannot extract the keys from the TPM and use it somewhere else. Even if you have the highest privileges. And all these three information things are used to facilitate single sign-on on anything that's connected to Azure AD. So when you go to Office 365, it will automatically sign you in. It will use this primary refresh token. It will use the session key to prove to Azure AD that it has the session key. And then it can just sign you in and everything works magically. Of course, if we are actually on the device, we can also interact ourselves with the primary refresh token. And this is the whole thing with single sign-on, which has been true since ever and TLM and Kerberos. If you're on the device, you can basically single sign-on to anything that the user has access to. And the same is true for a primary refresh token. So if you have an application running on the device or a backdoor running on the device as the user, you can simply call some RPC protocol and say, hey, I want a cookie, which will let me do single sign-on in Azure AD. And if you ask for that, then the system will handle the whole flow of going to LSAS, talking to the TPM, and it will give you a cookie which can be used for single sign-on. There's two references here. One is the RPC approach that Lee Christensen blogged about. It just uses the correct RPC calls to extract this token. I also used a different approach, and basically I emulated the Chrome extension that allows for single sign-on, because Chrome doesn't yet do single sign-on natively. So I just wrote a small program which basically calls the same helper application as Chrome does and requests cookies that way. So just to demonstrate, if we want to use this tool that I wrote, I called it the road token, because you can get tokens with it. You first have to request a nonce once again, because every time you sign in with a primary refresh token, it basically asks for a nonce. And this you can just do from your attacker host. Then you pass that nonce to the road token tool, and the road token tool will call the Chrome helper, which is just an executable on disk. It will send the request, and the system will process that and gives you basically a cookie that you can use with Azure AD. So here we see that I'm using the primary refresh token cookie, which is a signed cookie containing the token itself and a signature that it was that's calculated with a session key. So this is the cookie that allows for sign-in, and you see that this issues a token, even though I requested this on a different machine. But because I used the single sign-on data from the actual host, then it passes validation and gives me tokens. And this is also just in JSON Web Token, so we can decode it, and we can see that Azure AD thinks this token was requested from a managed device that was also domain joined. So if you use the single sign-on token, Azure AD just thinks that it was actually from that device, and you can also bypass policies that require you to be, for example, on a hybrid joined device. This basically also works to satisfy multi-factor authentication, because the primary refresh token will often have the multi-factor claim like built in. So if you do single sign-on with that refresh token, then Azure AD will also think that you're using multi-factor. All right, so this is from a regular user session. If you have administrative privileges, it becomes a bit more interesting. So I did some research on this back last summer with Benjamin Delphi, known very well as the author of Mimikatz, and basically built a combination of Mimikatz and row tools together that allow you to interact with this primary refresh token. So if you use this Mimikatz plugin, it's called the Cloud AP plugin, and it will dump like the primary refresh token information from LSAS. Now, if this primary refresh token is not, or the session key is not stored in a TPM, then the token will basically be in LSAS, and you can just steal the refresh token, steal the session key, and then you can use that wherever. Of course, if the token, if the private session key is in a TPM, then it's not in the LSAS process, and Mimikatz also can't dump it. So then what? I really started looking at how this interaction with the TPM works. I did a lot of difficult stuff with reversing WinDBG, but in the end, it was quite simple, or rather relatively simple, just monitoring calls to all the crypto APIs using API Monitor, which is really an awesome tool. I eventually found out that it uses the function an encrypt key derivation. And when I looked what this does, it actually says, all right, this function creates a key from another key. And the function returns a key in a byte array. So what does it mean? That it basically takes the key that's in the TPM and it derives a different key from that. But at that point, this key is no longer in the TPM, it's in the else-has process. So that's quite interesting for us. Just to put the flow a bit in context, how it actually works is it generates some random bytes, and this is called the context. And it puts the random bytes, it submits it to this function, and then a key is derived from the session key. So it basically talks to the TPM, and it says, hey, here's some random context, now give me a derived key from that. This derived key is used in combination with the primary refresh token to sign the JSON web token, and that together, that's the primary refresh token cookie that we can actually use to sign in. So this whole cookie, this whole piece, that's what we are actually after. Now the interesting part, if we look at this from a perspective where we have the else-has process on the left and the TPM on the right, then else-has is sending this random context to the TPM, and the TPM basically gives us back a derived key. And this key is used in the else-has process to sign whichever we want to use. But the thing is, this else-has process, that's running a software, so this is what we have full control over. So what is stopping us from actually just sending, requesting random contexts from the TPM and getting like 100 derived keys that we can then use to actually sign primary refresh token cookies whenever we want? Well, turns out there's nothing actually stopping us from doing that. So Benjamin made a nice function in Mimikatz. You give it the key material required to talk to the TPM, you give it a context, and it will give you back the derived key. And if you do this like 100 times with different random contexts, you can just get a list of future context derived key combinations that you can use many times in the future to use that same primary refresh token. We then go back to road tools. So there's this once again the Python code that I wrote to actually use this. And you can then submit the primary refresh token cookie, but also the context and the derived key. And then it will automatically unpack the cookie, request a new nonce, put the new nonce in the cookie, and re-sign it using the context and the derived key that we obtained. So to summarize this a bit, if we're administrator on the device, we can steal the primary refresh token and the session key if it's not in the TPM. If it is in the TPM, we can still require as many context and derived key combinations as we want, which actually allows us to use the token indefinitely without needing access to the device. If you want to read the longer version about this, it's on my blog, and there's also the details of all the reversing that I did to analyze this. So this was basically my summer holiday last year. Going actually to places is more fun, I can tell you. So after that, there was some more research that I did. So let's talk about how we can actually move further with this. So there are some downsides on doing this attack, where we need to be administrator and steal the tokens from the TPM. First, of course, we need to be administrator. Not all users are administrator. You need to actually dump else-has, run Mimikatz. That's quite noisy. Most endpoint protection things actually try to prevent you from doing exactly this. And if the primary refresh token expires, we can't request a new one because we don't have the private key material for the transport key or the session key itself. Also, if the device is disabled, then our primary refresh token loses its validity as well. So there are some downsides to this. So I came up with something new, and we're basically combining the two things that we just talked about. Like, we know how the registration flow works. We can register our own device, and that would give us a primary refresh token. And we know how to get an access token as a low privilege user by using single sign-on. So I thought, what if I register a new device using single sign-on? Would that work? Well, the answer is it does. So this is how you do that. Basically, you request a single sign-on token, which is specifically scoped to the device registration service. So normally you would authenticate with your username, password, and MFA, and then get a token for the device registration service. But if you're already on a device, you can just use single sign-on and request a token for the device registration service, just as you would for basically any other service in Azure. Then I wrote some other tools to actually register the device, so to do the whole flow of creating a certificate and then submitting the right request, which is all partially adapted from the AAD internals module by Dr. Azure AD, which is some really great tooling if you're into Azure AD hacking. But this basically takes the token for the device registration service, submits the request using a private key that it generates on the fly, and then it gets back the signed certificate from Azure. So at this point, we have our own fake device with the key that we control, with the key that's not in the TPM, and with the key that's not on the endpoints anymore that's heavily monitored. Now the next step, we obtain a primary refresh token. We can do this using only the username and password for the user. And if we do that, we get the primary refresh token, and we get a session key, which we can decrypt because we have just registered our own device with the key material that we own. When you use this with Row tools, you can once again request a token for whichever service you would like, using the primary refresh token and the session key that we have. So this just gives you a token for basically anything that you would want. Now the fun part is, you can request single sign-on tokens as a limited user. These access tokens, they will contain the MFA claim because the user performed multi-factor authentication at some point. If you then use that single sign-on token to register a new device, you will also get a primary refresh token, which also has that MFA claim. And we didn't use MFA at any point of this. We just used a single sign-on token, and we used the username and password. And in some cases, you don't even need the passwords, because if you use federated authentication, you could use NTLM or Kerberos to ask a SAML token and use that to register your device and get the primary refresh token. So we only did some single sign-on, and we got a free primary refresh token with multi-factor authentication from a limited user, which is pretty cool. Some upsides and downsides of this technique. It is separate from the old device. So if you disable the old device, then nothing really happens to our token. The primary refresh token will keep working because it was registered on a new device. And of course, it doesn't have to be like a physical laptop. I did this with just a script, and with the script, you can just store the private key on disk. Azure doesn't care where you store the private key. There's no way to prove that it's actually in a TPM. So it doesn't matter. You can just use it for as long as you want. You can refresh the primary refresh token for as long as you want, and it's all coming from like a legitimate device as far as Azure is concerned. Of course, there are some downsides. It does actually require you to be allowed to register devices. This is not always allowed, but a lot of organizations allow it. It's allowed by default, and it's required for some for the self-registration flow that's used with Autopilot, for example. It doesn't mean just because you register a new device doesn't mean that it's also allowed to write and roll in Intune, so it doesn't necessarily pass the policies that you may have which require device compliancy. There's some ways around that sometimes, but it may be prevented by some advanced controls. Now, if we actually have done all this, we can also, of course, use the primary refresh token using a Python tool. But that's not really useful for the attacker because it's like a lot of tokens and manual stuff. So I wanted to automate this. And we talked about the Chrome approach first, and Chrome actually calls a binary called browsercore.exe when it does single sign-on. So I just replaced the browsercore.exe with browsercore.py, which of course contains the primary refresh token data and some references to the RoTools library, which can automatically create the cookies and sign all of them. And if you then change the link for basically the Chrome extension and make that point to the new binary, then whenever you use single sign-on in Chrome, it will call the Python script and it will just request single sign-on cookies from there. And this works really well. If you just go to office.com, it will automatically call the Python code, use the primary refresh token, it will sign you in, and Azure will think this is from a legitimate company device, and it will also think that you used multi-factor authentication while in fact you didn't. So of course I reported this to Microsoft in December 2020, and well, there was some, it took them a while to fix this because it's of course not as easy as just blocking single sign-on tokens. They accounted for a lot of scenarios, but the final fix is actually rolled out earlier this month, which is really great because it means I can actually have this talk. And they also, I think they also rolled out some intermediary fixes for Windows specifically, but I was told this was also an issue like on Android and iOS, even though I didn't test it myself. So after the changes, it's no longer possible to use single sign-on tokens to register a new device, which is, I think, good, because there's really no reason why you would, why that would be a use case. There's also been some other changes. As I prepared for this talk, I noticed that there were some new flows for device registration. So this worked basically up until August, this flow that I just described. But on the latest version of Windows, if you have the August 2021 updates, it actually, well, Mimikatz doesn't work anymore when dumping the clouds plugin. Not sure why. I asked Benjamin and he said, well, probably because they changed some ways of how it's stored in memory. And I think they also partially changed how the TPM is involved in signing like this whole cookie thing. So there's like a V2 key exchange method now. I have to research this and see if it's also no longer possible to like hijack the TPM flow and extract keys as you want. So I'm curious how they did that, but I don't know yet. So as a bonus, this whole scenario can also be used to bypass MFA if you have some administrative account privileges. Now, how does that work? If we look at the registration flow, like the legit registration flow, if you register a device using multi-factor, then Azure AD automatically sets you as an owner of that device. Then after you sign in again, then the MFA claim, which is like stored on the device, so the device will have a property which authentication methods were used to register it, and MFA is one of those. And if you then sign in for the first time, Azure AD will just copy the properties that were used during registration to your primary refresh token. So if you use multi-factor authentication to register it, then the first issued primary refresh token will also have the multi-factor claim. Now this is done because the user that registered the device, so the owner, is the one that's signing in. If the user is not the owner, then it wouldn't transfer it. So as we said, the MFA claim is copied, and if you use the primary refresh token then to ask for tokens, then the MFA claim will also be present on the token, so that you did multi-factor authentication once at the beginning, and at the end you can keep using it and don't have to enter MFA all the time. And there's a flaw in this one, and the flaw is here, because it really issues these tokens. It transfers the claim because the user is the owner, and the owner of the device is assumed to be the one that actually registered it. but it's not actually validated. So there's no proof that it was the owner, or that it was the owner because it registered it, or that the owner was like changed in between. And here's just like, you see the MFA tokens. So what you can do this, if you are someone who can edit the owner of a device, then you can just add like a new owner with the device that you just registered. You can do that using the Azure AD module, for example. So in this case, I'm just connecting to Azure AD and using the PowerShell commandlets to add a new owner to the device as a device admin. And now the device has 2 owners. It can also have 10 owners. And then if you try to do the same thing again, so requesting a primary refresh token, using only username and passwords, then it will automatically get the multi-factor claim also in the token. So if you have this account and you have some passwords for users, you can just request as many primary refresh tokens as you want, including multi-factor authentication claims, even though you never actually had the multi-factor authentication for that user. So I reported this in May, and well, there was some discussions because initially they weren't convinced that it was actually an issue. But after some discussion, they accepted this as a vulnerability in July, and they actually fixed it in August, so that was relatively quick. And now there's like no longer that the MFA claim is transferred if you request a refresh token after device registration. So they've really decoupled that part, which I think is good because it wasn't a very solid security measure. So what can we learn from this talk? I think one of the most important conclusions is that single sign-on still breaks security, even in 2021, as it has been for like forever. Some way to defend against this is to monitor for strange device joins, because users shouldn't be registering new devices every day, and certainly not with strange names or operating systems that you don't actually use, such as SUOS. It's a bit weird. And you should also limit device joining or registrations as much as possible. Like you could grant those permissions to a group and only put users in a group when they actually need to register a device, rather than having it enabled all the time. So to conclude, all the tools that I've shown are part of the Road Tools framework / library, which is open source, available on my GitHub. I don't have the tools in there yet for the device registration and primary refresh token things. I'll probably do that somewhere soon when I write a blog about this. If there are questions, welcome to ask, also via Twitter or just whenever I'm around here. And I do have quite some Road Tools stickers with me, so if you like stickers, then just come pick some up. Thank you.
Any questions? Yeah, well, why not? I'm just curious to know if you think that this stuff was ever been used in the wild to bypass the MFA for some Azure AD using companies.
You would have to ask that to Microsoft. I don't know.
Okay. Any other? That's cool. Okay. Thank you, Dirk.
No problem.
It was really cool. Thanks.